So here we are. We're going to take a look at problem set 11. Specifically, we're going to kind of focus in around specific questions that people might have. The one that we'll wind up kind of ending on is problem number, is it number 6? Is that the Hey Jude problem, I think? I think it's number 6. So we'll do that. You okay, Emma? You going to make it? Must be good. Okay. So aside from number 6, what do people have questions on? Or was everything just, yep, I agreed completely?
I think across the board, people were struggling with 3, but other than that,
3? Which one was that? 3, 3, 3. Ooh, okay.
The one where we had the 2 things for the external.
Mm-hmm. And there's actually kind of 2 methods that you could use to do this one by hand, come up with a general solution by hand. One method is kind of brute force, try to come up with a guess that will work in one fell swoop. That's one way to do it. The other way is to say, look, I've got technically 2 terms in my forcing function, so I can kind of ignore one of those, do the guess for that part, and then ignore that one and do the guess for this one. Like literally treat them as kind of 2 separate problems. But notice both of those, whether it's together, both terms together, one term separate or the other term, whichever forcing function you have, that doesn't change the harmonic oscillator, the other side of the equation. So let's take a look at, see if I can make my camera work here so I can show you what I'm talking about. So if I remember correctly, it was, I think, y double prime plus 6y prime plus 8y equals 2t plus e to the t. And what I'm suggesting is you could do this, solve the problem this way, kind of ignore that, find the particular solution for this, call that y sub p1. And then if you wanted to, hold on, let me get rid of that stupid, you don't need to see all that junk in there. And then if you wanted to get rid of, not get rid of, if you wanted to, you could do the solution, oh, no, not for this, to kind of skip that and to do that much as the solution, kind of not doing this part, and call that y sub p2. You could find your particular solution for each one of those, because the overall particular solution is going to be the sum of those 2. Right? So if you did go this route, what would you guess? What would be your guess for y sub p1? What would be a good guess for that one? There's your forcing function right there.
I think I did AT plus B.
Okay, so AT plus B. So you've got a t to the first power term and a t to the 0 power term, right? Does it work?
I mean, it worked for me.
It worked for you. Now, keep in mind, remember, at the end of the day, we can always just hop over to Maple and say, hey, Maple, can you desolve this whole thing, right? And so coming up with a solution so that we know what the solution is shouldn't be too terribly surprising. We should be able to see this part of the particular solution if it's in there. So those of you who did this already in Maple, what does this turn out to be? What does the particular solution turn out to be for part 1? Is there a t to the first plus a constant term in the particular solution?
Yeah.
What was it?
It was t over 4 and then minus 3/16.
Okay. So let's assume that that's correct. That is the beginning, or that is the y sub p, the particular solution for this first part of the forcing function. Now we can figure out what is our guess. What's a good guess for y sub p2? Well, the forcing function now is e to the t, so what's a good guess for that? Anybody other than Quentin? Yeah, here we go. So we could use A, or if you want to be, thorough about it, you could use a completely different letter. So for example, I could say it's C times E to the T. And if that's what you guess, remember we're ignoring this 2T part. What does the C value turn out to be if that actually does work? What does it turn out to be?
E to the t divided by 15.
Okay, so 1/15
Yeah, 1/15, yeah.
e to the t. So what I'm suggesting is, if we're correct, then the homogeneous part of the differential equation comes from this side, which that doesn't change no matter what. But the steady state part, right, not the natural response, but the steady state response is the sum of this and this. So what we should see, by the way, is once you've figured out that this part of the equation right here, that has a y sub h solution. And by the way, what is our y sub h for this one? What does it turn out to be? What's it equal to? We're going to have two eigenvalues. Just looking at it, that thing factors as +4 and +2. Does that make sense?
Yeah, I have k1 e to the negative 2t plus k2 e to the negative 4t.
I completely agree. It looks like we were right on the same page. So we have our homogeneous part of the solution, and we have our two parts of our particular solution. So we should be able to say the general solution is just the sum of all these. Y of t equals y sub h. I'll even color code it so we can kind of see where things are coming from. Y sub h. Oh, what colors did I use for this one? I don't even remember. Plus y sub p1 plus y sub p2. And so if I play my cards right, I should be able to just kind of write all those out and say my general solution is equal to k1 e to the minus 2t plus k2 e to the minus 4t plus my first particular solution, which is t over 4 minus 3/16 plus my second particular solution, 1/15 e to the t. Is that, in fact, what Maple says the solution is when we look for a general solution?
Yeah, I think so.
Can we be more specific on that? I mean, it's not like you're sitting in front of your computer where Maple is.
Yes, that is what it says.
Is that exactly what it says?
No, actually it has a, the e to the negative 4t, it's
This
over, yeah, it's negative and it's over 2.
What do you make of that?
Well, I just think it's kind of lumped into our k2 multiplier.
Yep. It's just an extra constant for some reason, and we can go into what the reason is in a second, but for some reason, Maple's solution method leads it to have an extra -1/2 factor on this term. But of course, because K2 is a constant, we can just absorb that into the constant term. And yeah, that's the exact same answer. As long as these other terms look the same, then we're in good shape. Now, where that extra -1/2 factor comes from, I actually posted a Maple document that kind of goes step by step and shows you where that comes from. It actually comes from the fact that the original differential equation is a second order differential equation, and Maple uses an old pal of ours to solve this. It uses the integrating factor method, which we haven't thought about in a while. But the integrating factor method, remember, was a way to kind of undo without doing any differentiation. We just have to figure out what integrating factor works over here. You multiply through, and then it's magic. Well, because this is a second order differential equation, there's actually two integrating factors. There's one you use one time, and then there's another one you use a second one to do a second integrating factor method. And then when you're done with that second integrating factor method step, you wind up with the general solution. But along the way, it just part of the structure of the process, it picks up this extra -1/2 power. or not power, a factor that gets multiplied through. It's no big deal. But really, it's the exact same solution. We came up with the exact same solution that Maple would come up with. So I'm curious, Quentin, was it this part, or was it kind of justifying where that -1/2 came from?
I think it was just people guessing because most other people were doing like them put all into one. Like it sounded like I was like one of the only people that did it this way.
Yeah, and by the way, if you wanted to, rather than guess separately like this, you could, if you wanted to, have one big guess and just have the guess be these three terms. A times t plus b plus c times e to the t. But you'd have to have each one of those terms. If you left off the b, it won't work. If you left off the a times t, it won't work. What happens if instead I decided to involve another factor, another term up here, sorry. What if I wanted there to be a t squared term? Like what if I made this p times t squared plus at plus b? What would I find out that p is equal to if I plug that in and use that as my guess for y sub p1?
Just zero.
0.
Yeah, it would just turn out to be, oh, p is equal to 0. It works because it's possible that you could have a t squared term. In this case, it's just coefficient is equal to 0, so it's no big shakes. So the good thing about this method, the lucky guess method, is that if you make a guess and it works and some of your terms just are 0, then that means they're not necessary in your guess. That's okay. The problem that people run into is when they make a guess, but they don't have enough terms. And then they find out when they follow the procedure, they find out that that guess can't work. That's because you're missing something, right? So whenever you have a guess that doesn't work, you wind up with like 2 = 0 or something, or even something ridiculous like 0 = 0, which is no help at all. That's telling you you're missing something. You're missing some term in your guess, or sometimes a factor in your guess. So I think that takes care of number 3, at least the hard part. For part B, that's just throw it in Maple and let Maple tell you what the particular solution is. And then the long-term behavior for part C, what do you do there? If I want to know what the long-term behavior is for a solution, what can I do?
Can plot it.
Plot it, look at it graphically. Another way you might go would be to do what?
I just set t equal to infinity, and I kind of got that the first and last terms go to 0. So
Yeah. You basically go, hey, if t goes to infinity, you're basically making a limit argument, right? So the long-term behavior, that's code for as t approaches infinity, right? And so you can use that to your advantage. If you run into a situation where you've got the equation and it's sitting there in Maple, you can just say limit as t approaches infinity of that thing right there. And Maple will tell you what it's going to do. That's handy. But as Chris suggested, sometimes it's nice to be able to see graphically what happens to a solution curve over time. Right? You can, maybe get a sense of what's going on. The nice thing about the limit is if there's a numerical value that it approaches, you'll get the numerical value, as opposed to a graph, which sometimes you get like, it looks like it's going here, but I don't really know. I have flashbacks to Calc 1, right? When you learn limits and you're like, can't we just do everything with graphs, please? Do we have to do this algebra bullshit? The answer is, well, sometimes, yeah, you have to, right? Algebra is great for making particular, guesses or not particular exact answers. Graphing is great for approximations. Right? So sometimes approximations are good enough, but sometimes, like Wyatt, it's just not good enough. I don't know where that came from. I just happened to look down and you were right there. So, okay, so that's number 3. What other ones we're giving people pause? Anything else?
For me, a little bit with 4.
Okay, what about it?
When finding the solution to the related homogeneous part,
Okay.
it was a repeated eigenvalue of -1. And I noticed that, like, when I looked back at like an example to like make sure I was doing the right thing, I noticed that we never did an actual repeated eigenvalue problem when it wasn't in a matrix form. So like I
You're
wasn't
absolutely
sure.
right.
Yeah, I wasn't sure what the solution
There
would be.
actually is an example when it's a repeated eigenvalue, not in matrix form. It's just in the end of 3.6. It's one of the three possible cases with damping. It's the case where you have critical damping.
Oh.
Right.
Right. Yeah.
Does that
Okay.
make sense? That's exactly what it is. A critically damped situation corresponds to what we might refer to as a repeated eigenvalue. Now, you can still use the ballot if you want, but you'd have to turn that homogeneous differential equation into matrix and get the coefficient matrix and then do that. Or you can just flip to your 3.6 notes and go, so what happens in the case of a critically damped harmonic oscillator? And there's a pattern for you to follow right there.
Okay. Yeah, I didn't even think about the
Yeah, that's
critically
okay.
damped.
Part of chapter 3 and chapter 4 is this arc where we're seeing all of these different ways of thinking about solving problems really boil down to the same thing. It's just thinking about them in different ways. Sometimes it's easier to manipulate a matrix. Sometimes it's easier to just jump right straight ahead to the solution, right? With matrices, doing forced harmonic oscillators, it's really not fun. Unforced harmonic oscillators, no problem. But forced harmonic oscillators, you don't want to do that with matrices. It's ugly. Others? Anything else? Okie doke. So what I want to do now is I want to take a look at number 6, which is that marching band problem. And I want to specifically kind of focus in around what makes a good answer, or what would make a good answer for this question. So, hey, Jude, quit stomping your feet. This, by the way, is one of those, like, I don't know if there's any truth to it at all, but it's so commonly reported amongst people who teach this subject that there probably is some really like loosely connected basis for this story. And by the way, the college or the university in question, to my knowledge, is Stanford University. So, and I have a friend of mine who's on faculty out at Stanford. And so the last time we went to visit, I asked to go to the football stadium and check out the football stadium because I wanted to see if it's like, is it like unusually constructed? Is there something weird about it? And the answer is no, it's just kind of small. Stanford doesn't have a huge football stadium. And their marching band is notoriously kind of wacky. So they all the uniform for the marching band, that's the Stanford marching band, is basically dress however you like with as loud a colors as possible. So people wearing tie dye and doing all kinds of crazy stuff. It's a very unusual situation. But I'm particularly interested in what makes a good solution, or what makes a good explanation for what's going on. What to include? What would you need to include here?
The frequency of the stomping is likely close to the resonant frequency of the stadium.
Okay, so the frequency of the stomping, which we could call the forcing frequency, that's the stomping, is really, really close. It's approximately equal to the natural frequency, and that would be the frequency of the stadium. So in this event, it's important that we kind of connect some things here. It's important that we realize that the stomping of the feet, that's the forcing function, right? That is the outside force. And the stadium is the harmonic oscillator. So in a good explanation, the person responding to this question would not start off presuming that everyone reading this knows exactly what is going on in their head. They would start off by saying something like, well, if we think of the stadium as the harmonic oscillator and the people stomping on it as the outside force, that stomping as the outside force. Da, 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 da. So the setup is important. So what counts as what in our model? What is our model, or how is our model reflecting reality in this situation? Does your answer include that information? Does it connect the model pieces with the physical world pieces? If it doesn't, then it's not that strong. What else might we want to include?
Should we say that the frequency of the stomping is close to the frequency of the stadium, so it approaches resonance?
Ah, okay. So because of this, a consequence of this, we would expect it to approach resonance. There's one piece of the puzzle, though, that's a little absent so far. If this forcing function and the natural frequency, the forcing function frequency and the natural frequency are close to each other, we can expect resonance, but there's one more catch. There's one more thing that we've kind of not mentioned so far. What else must be true in order for us to think about things being close to in resonance or approaching resonance? I'll give you a hint. It's a feature of the harmonic oscillator that should either be not there at all or minimal at best.
How about the damping or?
Because resonance, at the beginning of section 4.3, we start off by saying, let's assume that there's no damping. Or failing that, let's assume that the damping is really, really small, slight by comparison. So the key here is it's not just a harmonic oscillator, but it's a harmonic oscillator with minimal damping. That's another feature of your answer, that if you don't have that in there, then you're neglecting an important part of the definition of when can something be in resonance or approach resonance. An oscillator can only approach resonance if its damping is sufficiently small at the same time as the outside force has a frequency that is really close to the natural frequency of the oscillator itself, right? Anything else that we should maybe mention in order for us to kind of have what would count as a good answer? Now remember, this is me, right? I'm the one grading your paper. You know me. I'm picky. I like to be like, well, technically this, right? So let's do what you should always do when you're coming up with an answer. Let's say you've got this much written down, at least in your head, and you're like, okay, I'm going to weave this all together. Let me go back and take a look at the question and make sure that I'm actually answering the question. It says, give a plausible explanation of the stadium's violent reaction to the stomping accompanying the song, Hey Jude, and to no other song that they play. So what part of the question have we not really addressed?
Why it doesn't happen with other songs?
Why is it only Hey Jude? So we've got the forcing function being the stomping. We've got the natural frequency being related to the stadium. We've got minimal or no damping. There's definitely damping on a stadium like that, but maybe minimal damping. And the consequence of this is that we expect it to approach resonance. And that resonance you could connect with this violent shaking of the stadium. But the one thing that we have not addressed at all is the actual song. Why is it Hey Jude and not others?
Because the tempo of Hey Jude is very particular, causing people to stomp at just the right frequency.
And so this is the key to the entire problem. The question is, why Hey Jude? And if you're talking about stomping, then you're not connecting those two pieces. Hey Jude inspires people to stomp because they're following the rhythm of the song. Now, how many people have actually heard the song Hey Jude before? Have you ever heard the song Hey Jude? Okay. You probably have heard it. You may not remember it, but it's probably one of the most famous kind of like that's what I'm looking for. Sort of party anthem Beatles songs. It's got this refrain at the end. It's like na 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 na. Hey Jude. That's the end of the song for like 2 minutes. They do this over and over, and people are like na 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 na, and it's got this very poo, poo, poo. And so at that particular tempo, the consequence is maybe this thing is at resonance. So the key point for us to remember is the song tempo leads to the stomping frequency. So why Hey Jude? I don't know. Maybe there's something special about Hey Jude. Is anybody thinking what I'm thinking right now? We're all sitting at computers with the ability to hop on Google and ask Google any question like, what's the tempo of Hey Jude?
74.2 BPM.
I'm so glad you looked it up. I figured somebody was going to.
I threw
It
it in
turns
my-
out that the song tempo, which according to, I don't know, some website somewhere, is roughly like 74.2 BPM. What is BPM?
beats per minute.
Beats per minute. Could we turn that into a more science-friendly measurement of frequency?
We can, but I was too lazy to do it.
What would the science-friendly measurement be?
Hertz.
No, not in terms of numbers, but what is it that we want to turn it into?
Hertz, right?
Hertz. Yeah, it hurts. First time anyway. So what is this in hertz? 74.2 beats per minute. This is per minute. We want to turn it into per second. So what is this per second?
1.237.
Yeah, that's what I got.
Sounds about right to me. About 1.237 beats per second is what's going on. Now, if you think about, that's about a little bit faster than this. It's not a particularly fast song. Think about all the songs you might have heard a marching band play. Think about all the songs that might have inspired people to stomp and clap in the stands of a sporting event. Does that sound like a typical tempo for those type of songs? Or maybe you've never been to a sporting event because you've spent your entire life in COVID times. There was a time when large masses of people would get together physically in the same space, sometimes sitting right next to each other, shouting loudly, the mouth rain falling all around them.
That just sounds awful.
Those were the good old days. But honestly, some of you I know were in band. I know some of you even played the trumpet. Did you do marching band, Esteban?
I did, yeah.
So does that sound like a tempo for a marching band anthem that will get people to start stomping in the stands?
Yeah, that'll get people, like, it's the faster stuff that people, like, really get crazy about. Stuff that's
Yeah.
slow or something, they really don't care.
Yeah,
Like,
people are like,
we played Jurassic Park one time for our marching band thing, and, like, nobody cared about it. And then you play Seven Nation Army, and everybody's going nuts.
dun, 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 dun. That's like here.
Yeah.
People love that. So what is it about Hey Jude unlike others? Well, maybe it's just one of those rare songs that's a slower tempo that people still want to stomp their feet. Do you see the difference of just leaving off right here in your answer and being technically okay, you're connecting some of the pieces with respect to resonance. And then when you do this, you're actually starting to answer the question. But going one step further and saying, hey, I think it's because Hey Jude is one of those songs that apparently people like to stomp to, even though it's slow. Maybe most slow songs people don't like to stomp to. That's taking it one step further. That's answering the question and speculating. Notice it says give a plausible explanation. It doesn't say what's the right answer. It says what's a reasonable, plausible explanation for what's going on here. So just saying, oh, the stadium is like getting close to being in resonance, that's not really answering the question. Got to go one step further. Does that make sense? Yes, no, maybe so. Do you see the difference, kind of the different levels of the response for this question? You can almost see in my crazy brain who's going to get the highest marks for this problem, who would get the next highest marks, and who would get the next highest marks, you know, all the way down. And so for this, that's a good example of like an 8-point problem. And if somebody said all of that and came to the conclusion that, hey, for some reason, I think a reason might be this, Hey Jude gets people stomping, that's an 8-point answer, provided they figured out or they responded to the whole resonance and the stadium thing. But somebody who just told me the forcing frequency and the natural frequency are very close, that's like a 2 or 3-point answer. If you remember to tell me what the harmonic oscillator is and what the forcing function is, that's another point. If you remember to tell me that there's minimal damping, in order for us to really consider resonance as a possible plausible explanation, we have to kind of downplay the damping. And by the way, I don't have a good explanation for why there would be minimal damping other than buildings tend to be designed to prevent this sort of motion, especially like stadiums, right? Side to side motion. They tend not to be designed to prevent this sort of motion because they're presumed to be on pretty solid ground. So you don't need to worry about that. But if you're in between kind of two supports and standing on a beam, you get that flex on the beam. And so maybe that's what's going on. I don't know. So I'm pointing this out only because there may be a problem like this on the exam. And so when you're answering the question, take a look at the point value and say to yourself, this problem's worth 10 points. And I think I might have answered it in 5 words. Is that maybe an indication that I should go back and take a look at this a little bit more deeply? Should I be looking for more to the answer? Or should I even be rereading the question to make sure that I'm answering the question? Did you catch it was very subtle. I don't know if you caught it. Right? I'm winking at you. So I'm going to stop sharing the screen here. So now that we've lost Emma again, she just can't stick around for anything. Jeez. Hey, there she is. She's back. Emma, you're back. Okay, so Matt, explain to me the University of Wisconsin when they play jump around. What do you mean by that?
At the end of the 3rd quarter, start of the 4th, the stadium plays the song over the loudspeaker, and everyone in the stadium starts jumping. And you can, if you're underneath, you can watch the stadium flex like crazy.
Really?
Yeah, it's pretty nuts.
Could you hear audio there? I was going to play something, but can you hear something in the background or no?
No.
Okay. Hold on. Let's see if I can do this. I think I can do this. You dirty dog. Okay, let's see if we can get this Zoom room vibrating. You ready? Wait for it. Nobody remembers this is how the song begins. It's very boring at the beginning. It's like, okay, the house is a pain. House of Pain is in effect, y'all. That's the part everybody remembers.
It's really weird that that's not the start of the song.
Come on, everybody. Paul. Everybody jump. Huh, huh, huh. This is going on YouTube. Make it count. Matt, totally. Really? No, 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 no. Stop. Stop, 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 stop. Stop, House of Pain. Matt, you're not even in effect.
I might not have been searching for the video of the stadium flexing.
I believe it. This is what happens when you get a room full of nerds and you start talking about something interesting. People are like, oh, really? Hold on, let me see if I can find that. Yeah. This, by the way, this always happens in every department meeting. I'm in 2 departments, right? Science and math. And so if we get going in a department meeting and somebody's like, oh, did you hear about this one thing? Then you know everybody has got their phone out. They're like, nobody's listening to what's going on. You know, the meeting may as well stop until everybody gets it out of their system. Somebody can look it up and go, it's right. Look at that. Look, everybody look. So anyways, so that's good. Any other examples that you can think of harmonic oscillation and resonance in your everyday life, or, you know, interesting consequences thereof? Thanks, Bob. Anything else?
I got dinner.
Hey, all right. What are we having for dinner tonight?
Macaroni and cheese and stuff.
Wow. Boy, they're really splurging on you today. Is it the good stuff, the craft? Or is this like...
Baked in the oven with bacon bit and croutons.
So
and
it is good stuff. So that is the good
yeah.
stuff. Wow, that's really nice. Wait a minute. You're not playing me through the speakers so that your mom can hear me making fun of her cooking, are you? You better not be. Don't get me in trouble.
I wouldn't do that.
So an interesting thing happens when you start talking about harmonic oscillators. You start noticing them everywhere. So in electronics, for example, you can have circuit boards that act as harmonic oscillators, right? As you noticed in the problem set, one of the problem set questions was, what happens when you have a harmonic oscillator in the form of a resistor tied to an inductor tied to a capacitor? And if you haven't had any electronics yet, or electricity and magnetism, if those things don't make any sense to you, you could still solve the problem, right? It's still possible to solve the problem. But once you know what those things are, once you see it, you can go like, oh my God, the same underlying mathematical principle for how this thing behaves is the exact same thing that describes why a little kid on their swing set in the back can pump their legs and wind up going higher and higher and higher with a forcing function. It's the same mathematical principle. It's the same underlying principle as what explains harmonic oscillation of a spring or a building or anything. So the power of the stuff that we're learning isn't that you can do this mathematical operation to solve it. It's that you can apply it to all sorts of interesting contexts. And so one of the things that we're going to do now is take a look at the 4.3 classwork. And some of the questions in the classwork, 2 of them, I think exactly, have to do with what do you do in a situation where you're applying this harmonic oscillator resonance idea in a context that is not the same thing as what we've been dealing with. similar to our Hey Jude problem. How do you connect the dots? Well, one of the first things you have to do is say, here's my model. What am I going to plug into the model? What counts as my harmonic oscillator? What counts as the forcing function? Because if you can't define those, then you can't really use that model to make predictions. So what we're going to do next is turn our attention to, boop, boop, boop. I'm going to delete some rooms, and then we're going to reassign, boop, 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 recreate, and we're going to do 4 rooms, and I'm going to put you in there. We have a couple people in, or one person not with us today. Austin's not with us today. So we're going to combine our teams Brat and Team Ego. And so they're the bratty ego, I guess. So let's see, Wyatt and Steven, one team. Let's see who's next, Chris, Matt, and Bryce. And John and Quentin. Boop, boop, boop. And then last but not least, okay. So what I'm going to do is I'm going to open up the rooms, and you'll notice on the agenda that I've given you a problem from the 4.3 classwork. What I want you to do is solve that problem. And for some of you, that means doing some computation, doing some calculation. You can do stuff on Maple. For some of you, that means there's no calculation, but you do have to connect what the situation described is with the model that we know that we can use to make some predictions. So I'm opening up the rooms, and I want you to head in there, work on your problem. I'll be around. I'll check in on you. But we're going to get back together at no later than 7:28. So 20 minutes from, well, I'll check in. We'll see how we're doing in 20 minutes. And I'm going to hit pause on the recording. So we have had a chance now to take a look at the 4.3 classwork. And so now let us gather around and see what we can see. Who steps forth to claim problem number 1?
Wyatt and I do.
Yeah, that'd be us.
Together.
We
We
claim
have a-
it. Okay, fire away. What you got? So problem number 1 was a use only analytic methods to find a particular solution. And we know this is probably going to have something to do with resonance. So let's see what you got.
All right, so we split it between each other and stuff. So I found the Y of H, Steven found YP, and then I was working on the general solution when time ran up. So we haven't actually gotten the particular solution yet. So here's my screen so far.
Sure, parts is parts.
So this is what I got going. I looked at page 20 in the notes and stuff, and I got my Y of H, and this is what I got for my Y of H. Steven, this back part right here, -1/4 cosine theta t. This is the YP that Steven found, so this is our general solution overall. And then I was working on trying to find the particular solution when we ran out of time.
So where did the square root of 2 come from?
Square root of 2. Oh, I messed that up. Square root of 3. Square root of 3. I was looking at the notes, and it's square root of 2 and the notes and stuff, and it's square root of 3 in my copy. So
Tell her I don't want any ice in my soda. Thank you, though.
there we go. So that's our general solution. And still working on the particular solution.
So I have a question. Where did the square root of 3 come from?
So s squared plus 9 = 0, and then Steven did the s solve or whatever to get our square root of 3i. But then, like I said, I was just following the notes on page 20 and stuff and how we did on that.
Nope. I don't want you to just follow the notes. I want you to actually solve. You didn't actually solve it. There's no way Maple would have told you the solution for s squared plus 9 = 0 is plus or minus the square root of 3i.
Yeah, that's on me. I done goofed. I meant just normal 3.
It's on him. He wrote it.
Okay.
So the problem, my friend, as I may have mentioned once or twice before, the problem with doing all of your work in this lovely little picture is that you can't actually check your work, right? You're just recording what you did somewhere else. But if you don't show me what you did somewhere else, then I have no idea what's going on.
Okay.
So the downside with this is I'd look at that and go, now, where'd you get the square root 3 from? So what should it be?
Should be 3i.
Which is going to change a whole bunch of other stuff.
No, it doesn't want to.
As exciting as it is to watch you change this, Stephen, I'm curious, how did you come about your solution? So let's take a look at your particular solution process here.
So our particular solution is this, and I know this because I just typed it in while Wyatt was talking. So this is our final answer.
Okay.
As far as how we got there, because of course we did it all by hand.
But with 2 T's. Nice. Well done.
My computer's drifting for some reason.
What kind of tires do you have on it?
I don't know. I think I should get them changed. Let me try.
It's those Yokohama racing tires.
Oh,
it gets my computer to drift all the time. That's crazy.
It's Maple's doing funky stuff. We're gonna try it anyway. Okay.
I heard the bass music.
Let's see if we just grab it kind of like that. Is that legible?
We can read the screen. Yeah, it's kind of like fluttering when you try to drag it down.
What the heck? Now I'm opening help menus and maybe my computer just started going nuts everywhere. So maybe I should not do this real quick, but I'll just read it off. Okay. So what we did was, let me get rid of whatever this is. Maple's currently trying to help me with the problems that it senses I'm having. So what we did is we did roughly the same technique that we used for problem 7 on the homework. And
okay, walk me through. All right.
All right. So we started off with, so I was in charge of y sub p. So we had it equal to cosine. So I did the y sub c stuff.
Okay. So what's our guess?
So our guess for y sub c was, one second, if I can find it, alpha e to the 3it.
Okay.
And then if you take that derivative, it should give you.
And just to be clear, which part do we care about?
What's that? Oh, we care about the real stuff because it's cosine.
So that's for later, just remember. Okay,
Yeah.
And so first derivative becomes?
First derivative becomes, well, I just skipped right to the second derivative, which was -9 alpha to the it, alpha e to the 3it, yeah.
No, not to the 3i
right.
Raven. That's something completely different. We don't actually care about this because that doesn't appear in our differential equation.
We don't need it.
Cool. So our differential equation, the left-hand side, remind me, was y double prime. So that would be -9 alpha e to the 3it. And then what's the second term?
It should be plus, where to go? One second. The original, so alpha e to the 3it.
What's the differential equation, though, that we start with? Because we're plugging this back into, it's something times y. So what's the something here? What's the coefficient for that second term?
It is, one second, we'll get there eventually. It should be plus 9 times y.
So in this case, it would be 9 times alpha e to the 3it equals, the right-hand side of the equation is 2 times e to the 3it.
Correct.
Do you see the problem?
Can you move your mouse? It's a.
That wasn't where the problem was.
Oh, was it not? Dang, dude.
The left side's going to equal 0.
-9 alpha plus 9 alpha.
Do it.
We're going to wind up with 0 equals 2 if we factor away our e to the 3it. And that can't be possible. So this guess is wrong. Right? So in the event that you have a wrong guess, especially in this context, what do you do?
Just take the L.
Just take the loss and just be like, you know what? Screw it. I'm just going to like write down some gobbledygook and hope he doesn't notice. And then I'll just be like, and the answer is this, whatever Maple told me the answer was. No, what we can do is we can change our guess up. And instead of guessing E or alpha times e to the 3it, we're just going to multiply it by t. We're going to say our complex guess is going to be alpha times t times e to the 3it. And if you do this, then it definitely does work. As a matter of fact, this is the only way you can analytically solve a resonance problem, because that's what's going on here. This sucker is in resonance. And how can we tell that it's in resonance? By looking at our differential equation, y double prime plus 9y equals 2 times cosine of 3t. What's the relationship that's cueing us in to this being in resonance?
Is it because it's the root? Or
Hey, look at this. This thing is omega squared. There's omega. You see it? Because there's no damping, the natural frequency is just omega squared, or it's just omega, which is the square root of that thing. And so this forcing function has the exact same frequency as the natural frequency of the oscillator. And so that's a problem. And this, by the way, ties in nicely with our next problem. So if you can follow through with this guess, or let Maple do it, and get your particular solution, and then write your general solution, use your initial conditions to find your overall particular solution, you'll find out that it is a resonant situation where if you let t approach infinity, your amplitudes take off. They grow in both directions. So I don't want you to follow like it's a cookbook, previous problems. You can use them as kind of a wayfinder, but every problem in here is going to have some similarities, but the similarities aren't in the number level, right? They're not at the level of, oh, always guess with a 3 up there. No, you only guess with a 3 up there because there is a 3 in the cosine. That's what determines what our guess is going to be. So you got to recognize where the patterns are. Sometimes they're a couple layers underneath. Cool. Again, this is the spot. This is where we get to help each other stand up, brush ourselves off, and go, I'm not going to fall for that pitch again. Okay, good. So on the exam, you won't get stuck on this one. Yay. How about number 3? Number 2. Who had, not number 3, number 2. Who had number 2?
We did.
I'll give you some intro music here. Hold on.
Oh boy.
No, I'm not going to do it. I'm not going to do it. Just because you said that, I'm not going to.
So for number 2,
Mhm.
we were just kind of showing how to get to the omega value that would cause resonance. So we just looked at getting y sub c for the problem, like as if you were solving it. And we ended up going through the process, finding our y prime or y double prime, substituting into the equation, and basically solving for alpha. And we get the 1 over negative omega squared plus 5. And from that, we can see that it would equal 0 or be in resonance. The denominator of that would equal 0 when omega was equal to the square root of 5.
Nicely done. Yes. Spelling it out in full detail. Now see that this is clear in terms of the step by step based on the problem solving process. You can see that omega equals root 5. That's going to produce resonance, and they even explain why, because of course that's going to produce a 0 in the denominator for the amplitude, right? So it's going to blow up the amplitude part of this thing. And so that's a much better explanation than my sort of ham-fisted, I just basically said, there's omega squared, right? And is that backwards? I don't know. But that's sort of a ham-fisted way of doing it. But this is a much more thorough answer than mine. So nicely done. Good job on that one. Any questions on that? No? So I think we could clearly say, word to your moms. They came to drop bombs. They've got more rhymes than the Bible got Psalms. Okay, number 3. Who's got number 3?
Team I don't know does.
I don't know. Okay. What you got for us?
All right. So we were given that the natural period was 2 seconds, and then the car is going 20 miles per hour. So we had to figure out the distance of speed bumps to make it violently, increase in amplitude or whatever.
One might say jump around, but yes.
Yeah. So first we thought we had to do something with the frequency, since we were talking about it before, where the natural frequency has to equal or be close to the forcing frequency for resonating, but it turns out we didn't have to do that. So here we just converted the miles per hour to miles per second, and then here we converted it to feet per second, and then down here we did that times the period to get rid of the seconds, which ended up giving us 176 divided by 3 feet, or 58.667 feet.
So what you're saying is, as the civil engineer designing this neighborhood street, imagine, if somebody says, we want more than just a sign that says, thou shalt not go faster than 20 miles an hour. So we want you to design the road in such a way that more than just a sign prevents people from doing it. And you say, yeah, I think I got something. If we set up speed bumps, we can kind of enforce the policy by physical means. Because if you try to drive faster than a particular speed, these bumps are going to really hurt your car. And so they figured out that if you place the speed bumps about 59 feet apart, that somebody who's speeding up and going about 20 miles an hour, once they run into this, that's going to be a problem for them, because the wobbliness of the car is really going to start to amplify. Cool. Do you think it's that simple in the real world?
No.
Not quite, but it's actually the same principle. It turns out that all you need is the distance of the wheelbase for a typical car. And if the distance for a wheelbase, which is not exactly the same, but similar, a lot of cars have very similar wheelbases. If you know that distance, you can actually figure out about how quickly would the car have to go over bump in the front, bump in the back, in order to create, in essence, a kind of resonance. And so you can figure out about how big a speed bump you have to have in order to generate resonance-like behavior in a vehicle going at a particular speed or above. This is why, I don't know if you've ever noticed, but if you take a speed bump too fast, you can really screw up your car. But going much slower, it's not a big deal, because of the way the springs in your suspension are designed. They can handle that compression at a slower pace. But if you compress it too quickly, close to that natural frequency, bam, you're going to break your suspension. Interestingly enough, you can go super fast over speed bumps and you'll still ruin your car. Don't do that. It's bad to do that
That's
anyways.
how I do all my speed bumps.
But you can actually go super fast over a speed bump or a set of speed bumps, and it will be not as dangerous for your car. I'm not telling you to do this. I would never tell you to drive way over the speed limit to try something out as an experiment. But if you do, you'll discover, oh, that's one way to take speed bumps and not have to worry about taking damage. Just go quite a bit faster than the suggested speed limit. Don't do that. That's bad. Okay, how about number 4? Let's make Emma do it. No, her internet is like approaching robotic levels of. She sounds like a
Okay, I'll share
transformer.
a screen, show what I have. We didn't come up with a whole lot. So we basically came up, okay, well, we have a goblet, and when you're rubbing your finger around the outside of the glass, it produces a very loud, clear, single pitch note. And so we figured that the outside force was the finger rubbing on the rim of the glass, and the glass was kind of the harmonic oscillator. And so we kind of figured the frequencies would be equal, causing the cup to vibrate, and so the system like approaches resonance. And there's also like minimal damping.
Okay, remember, you don't have to be exactly equal to the natural frequency with your forcing frequency. You just have to be in the ballpark. And if you're in the ballpark, then you start to get that spike in amplitude.
Yeah, I'm not sure. Is there something about it being partially filled? Does that have something to do with it?
Yeah, so basically by changing the level of water in the glass, you're changing the natural frequency.
Okay, that makes sense.
Yeah. So by changing the level of water in the glass, you're affecting what the natural frequency of the resonator is.
That's true. I remember that from the video. Yeah. Yep. That's about all we came up with for that one.
Cool. So again, the last 2 problems are really me just trying to push you to think about resonance in some different contexts. That's not just a standard mass on a spring, right? So thinking about it in different ways. And I don't want to spoil the ending, but I've got another one for you on the exam that's a little different still. It's not quite something that we've done before, but you can use the same principles to kind of get at this idea of when would you expect there to be, if it's at all possible, when would you expect it to approach the state of resonance? And so what do you have to have happen in order for that to occur? So the link that's on the PDF document, if you get a chance to watch it, it's actually kind of an interesting video. The other thing that I would draw your attention to, let's see if I can get the, oh God, it's stupid political ads on YouTube. It's really annoying. Hold on. I got to wade through this crappy blah, blah, blah. I'm going to pull up this screen so that we can all take a look at it. Once I get through this stupid political ad. So hold on. Hold on.
Benjamin Franklin saw someone playing a set of water-tuned wine glasses and thought that this would be a more convenient arrangement. He wanted to do away with the water tuning and wanted to have a lot more glasses and be able to play more than 2 at a time. So voila, one of Franklin's favorite inventions.
So just to be clear, Ben Franklin invented this. One of the other things that he did, in his spare time. It's basically a series of bowls that are tuned to just the right pitch, all kind of tipped on their side and kind of nested inside of each other. They don't touch, but they're on a single pole that rotates at a particular speed. And so the guy who's playing it, all he has to do is have his fingers dampened, and he can touch the bowls and make them resonate at particular pitches. And he basically is playing it like a piano, right? Essentially. But instead of hitting a string to vibrate, he's getting some kind of resonant pitch for each one of the bowls.
So these are all basically custom blown wine glasses, and they're all nested inside of each other. And the whole
Didn't I just say that?
is turning, so you can play it somewhat piano-like.
So he's got a bowl of water underneath and he dips his fingers in there. So an interesting question is, what the hell is causing the vibration? He's wet his fingers down. Isn't that like make things glide and smooth? What's going on to cause vibrations in the glass?
He's mastered the ability to really finely hit it, just really fast, but just
Just
so
pull.
fast that we can't see it.
Well, he's not hitting it. And in order to do this, have you guys ever done this with a glass at a fancy restaurant? You can start doing that and really annoy people. It's great. It's one of my favorite things. Whenever I get dragged to a fancy dinner, I just like, start making little. You borrow other people's glasses and make noises. You're not actually hitting. It's not percussion in that sense, but it still is creating a force, a periodic force. So what's periodic about touching the glass?
Don't your fingers kind of like bounce up and down just a little bit, but very slightly?
If you
I
get
feel
really
like
close to your fingers, one of the things you'll notice, not that you can see it on mine there, because I have burned all of my fingerprints off, is that you have little ridges on your fingers. We call them fingerprints. And those little ridges, if you kind of pull one finger just lightly across another, you can feel it kind of grab and let go. And so you wind up feeling like this kind of like as they sort of slide across. And that can be all the periodic force that's required to cause these glasses to begin to resonate. That tiny little itty bitty force of your little the ridge on your finger kind of grabs onto the glass and then releases it. It grabs and releases it. And that periodically happening at just the right speed causes the glass to resonate like that. It's fascinating. It's really, really fascinating when you think about. We take for granted the fact that, oh, it's nice and smooth. You run your fingers across the glass and it's smooth. But as you run your finger across the glass, there's a whole bunch of tiny little grabs and releases, grabs and releases, grabs and releases happening super fast. We don't even notice it.
Is that why you can't do it with like all glasses? It has to be like special types of glasses.
Yeah,
'Cause they have
special
different
types of glasses.
frequencies?
They have different frequencies, right? And we're talking about frequencies that that correspond with notes that you might hear as like a high A at something like around 600 or 800 hertz, which means that your fingers are grabbing and releasing and grabbing and releasing somewhere in the neighborhood of like 600 times per second. This is why we don't think of it as being anything. There's nothing periodic to what we're doing, but it's at the microscopic level where that forcing function is happening. Sometimes the model works, but the reality doesn't appear as obvious. Right? You have to look a little bit deeper to see what's going on. This is another kind of ties back into where we left off last time with those bridges, that the Tacoma Narrows Bridge that collapsed, because the engineers at the time were not considering the possibility of air vortices, kind of air blowing across a bridge, hitting this kind of flat surface, horizontal surface, and then kind of creating a vortex that when it sheds the vortex, it kicks a little bit. They're like, but that's not a big deal. It's just not a big deal. But if it happens over and over and over and over and over at just the right frequency, you can create a forcing function that's tuned to the natural frequency of your bridge. Amazing things happen when you're talking about resonance that are not always obvious or always easily predictable, right? So I like to kind of end with that as sort of an example of something cool, musical instrument, but a fascinating kind of like real world. There's physics going on, there's biology going on. Your vocal cords are another example of, resonant frequency. Your body's ability to control how tight those vocal folds are in your throat. that voice box that you have, is an incredibly complicated musical instrument. And your brain's ability to control all the tension in those vocal folds to produce sounds all over the place, right? People can sing super high notes and really, really low notes. That's pretty fascinating stuff. At least I think it is. And if you're really good, if you're an amazing musician, you can produce all kinds of cool stuff. Okay, that's it for today. We will end there, and I will say to you, you have through 11:59 to finish up the problem set if you haven't already. If you've submitted it and you want to make some changes, you can go back in and resubmit. I think I made it so you can submit up to 2 documents. So I'll just take whichever one is the most recent one, and I'll grade that one. So you've got problem set to finish up, and then tomorrow, probably later on tonight, I will send out an email with an attachment of the exam for you. I actually have to finish writing it, so I've got homework to do tonight too. So it's all no jumping around for me. Just Matt, like Arnold Schwarzenegger, which is the only other lyric in that song that I can ever remember. I'm like the Terminator, Arnold Schwarzenegger, and that's it. That's all I remember. I don't know what else they say. But there is a really weird coincidence where that song and the Bill Nye the Science Guy theme are really, really close to being the same song. You think I'm lying? Go Google Bill Nye the Science Guy theme song.
I really like when they overlay 2 songs with a really similar tempo, and it just really works together, but it shouldn't.
Yeah, I know. One of my favorites is that there's a Led Zeppelin song that they can lay over the top of a James Brown song. And you think, no way. But they totally work. It's amazing. It's just so cool. Okay, so that's it for tonight. If you have any questions, you can stick around. You can jump around. I'll be here for a couple minutes if you want to do that. Otherwise, finish your problem set and gird thyself. Prepare for the exam that's coming your way. Sound good? Quentin, are you in some like Blair Witch Project situation going on there? What's going on? You got me really scared. I expect to see like a pair of eyes behind you, like, and then Quentin's screen goes black. We never saw him again after that.
No, it's actually